Okay, welcome back everyone. We just have one more slide on Unit 6 to discuss, and then we'll move on to Unit 7. So in this last slide, we're going to talk about constrained optimization. So far in optimization, we considered unconstrained optimization, which meant that for the parameters, let's say W we were optimizing, we were putting no constraints on them. For example, we're not saying that they needed to be positive or they needed to live in a subspace or something like that. But when we go to this next unit, we're going to be doing constrained optimization, so I just wanted to briefly talk about it. So when doing constrained optimization, there's sort of two classes of things you can imagine doing. One is that you might have some equality constraints. So you have you can make some function, HL, such that when you apply that function to your parameters, you get 0. And this is, you can formulate any kind of equality constraint like that just by suitable choice of that function, HL. And here you can have up to capital L different equality constraints. So we'll talk about that first. And then another thing that you could have is you could have inequality constraints. So here we have capital M, different inequality constraints. Each one is that some function GM operating on your parameters must be less than or equal to 0. So those are a couple constraints you can imagine. And when you combine those with your optimization problem, you're doing something like this. You're trying to find the minimizer of some cost subject to all these constraints being in effect. And so this is a more difficult problem to solve than the unconstrained problem, but basically there are some strategies to do this. Let's first talk about what we do with equality constraints. It's actually not too complicated. What you do is you add additional optimization parameters to your problem. They're often written as lambda L. You add one parameter for every equality constraint, one lambda. And now these are going to be new optimization parameters. So now we're going to be optimizing over both W and lambda. And we're going to be optimizing a different cost function. This new cost function is the old one, J, plus a sum of lambda L times those equality constraints. And the reason that this works is, remember that in unconstrained optimization, so now this is an unconstrained problem. In unconstrained optimization, if you set the gradient of, if you want to find the minimum of a certain parameter, you can find it by setting the gradient to 0, right? So imagine that you do that with lambda L. You set the gradient of this to 0. So when you compute the gradient of this, you'll just get the function HL. And when you set that to 0, you get exactly the constraint you want to satisfy. So that's why this works. You just add these Lagrange multipliers, you add this additional thing onto your loss function, and then you solve this new unconstrained optimization problem that involves these extra parameters. So that's it in a nutshell. Any questions on this method? Okay. What happens when you have inequality constraints is very similar but a little bit more complicated. So basically you now add some parameters for the equality constraints just like before, and now we add a new set of parameters, mu, for those inequality constraints. But it's a little bit more complicated in terms of how to do the optimization. You have to check some particular conditions called the KKT conditions. We're not going to get into all the details of how to do that. If you want to learn more about that, there's some great optimization courses to take. I'm just sort of mentioning this to say that there is a solution to this problem, and just to kind of expose you to this idea, which we will use this idea in the next unit. So that's the case of inequality constraints. All right, so if you're interested to learn more, we have some great optimization courses. We have 5500, which is Introduction to Optimization, taught every autumn. We have a follow-on course on convex optimization specifically, 6500, taught odd years in the spring. And we have a more advanced course on non-convex optimization for machine learning, taught every 2 years in the autumn. And I think there's a number change in progress. I can't remember if there's a new number or not yet, but this is what it was called last time.
Are those all graduate courses?
Well, as you know, 5,000 level courses in this department are both undergrad and grad, right? So, whereas these other ones are probably going to be populated mostly by grad students. So it's not to say that an undergrad cannot take them. You just have to be aware that the course might be a bit more advanced. But if you've taken 5,500 and if you did well, then you could move on and probably take one of these. It's just an outgrowth. Okay. And then there's a bunch of stuff that's important that we didn't talk about. I'll just briefly mention. We focus on gradient descent, but there's another more powerful class of methods called Newton's method, where you can kind of think about it like if you were doing gradient descent, but you had a matrix valued step size. And what that allows you to do is it allows you, instead of how gradient descent kind of took a curved path towards the minimum, what it does is it sort of, it can sort of shoot right directly towards the minimum. And if the cost function is quadratic, it will go right to the solution in one step. The cost of those methods is basically, you don't just have to compute a gradient, you have to compute a Hessian matrix. A Hessian matrix is a matrix of second derivatives. So there's a computational cost to those methods. And then there's some methods in between Newton's and gradient descent called quasi-Newton. In some applications, they work well. Another thing we didn't really spend time on is non-differentiable optimization. We sort of focused on the case where we had gradients, we could do gradient descent. But there's definitely cases like Lasso where we don't have a differentiable cost function. And so in those cases, we have to use some other more advanced methods that would be talked about in these courses that use, instead of gradients, they use something called a subgradient and so on. Just wanted to let you know that it's out there. And then in terms of machine learning algorithms, we talked about gradient descent, we talked about Armijo. When we come to neural networks, I'll tell you a little bit more about some other options. But there definitely are many other options beyond gradient descent, things you can do to enhance gradient descent, such as adding momentum and so on. So there's a lot that we didn't talk about. We just talked about some kind of basic stuff. So that's sort of what I wanted to say about optimization. Any questions on anything? Okay, great. So in that case, let's move on to the next unit. So this unit is about support vector machines, and we'll also learn about, start to work on some image processing. So as our problem that we're going to focus on, our demonstration code and so on, it's going to be about digit classification. And so the idea would be that you are given an image of a handwritten digit. So these are various examples of what you might be given. And given that image of the digit, you have to predict what actual number between 0 and 9 that would be. And so, in many cases, it's an easy problem for humans, although, not all cases, because people write in different ways, and sometimes people are sloppy, and sometimes it's really impossible to tell what digit did they mean when they wrote that. But this is a very famous data set for machine learning, like kind of, you could say, sort of a toy data set by today's standards, but it's still big enough to be interesting. and certainly bigger than the data sets that we have seen so far in this course. So this is a data set that has images of size 28 by 28. So those are 28 pixels horizontally and vertically. And the pixels are so-called grayscale, so they're not color, they're just brightness values. So like white would be the highest brightness and black is the lowest brightness. Typically, the images are 8-bit images, meaning there's 256 possibilities for what the brightness can be. So it's a number 0 would be black and 255 would be the brightest white. That's typically how those images are stored. In this particular data set, there's 70,000 examples of these images. They were collected in the 1980s by the US government because at the time they wanted to transition the post office from people that were reading letters with their eyes to like computers that are able to just automatically decode the addresses and then sort of send those letters off to the right places without as much human intervention.
Can you imagine how long it took to collect every different,
Yeah, so that's definitely something we'll be talking about as we go further in the course. Is that one of the burdens of doing machine learning is making a big data set, and as we know, like there's big advantages to having a big data set, right? And so the better your model, the bigger your data set needs to be to train it. So yes, that's a good point. Is that this took some effort to to collect all this data, and that's true of a lot of data sets that we have in machine learning. They take effort to collect. But anyway, so by today's standards, this is small, but it is definitely famous. A lot of people have played with it. If you go on Wikipedia, you can find a page about this data set that has a table of at least, I don't know how exhaustive this is, but someone has been updating this table with the performance of different methods. And if you look kind of on the bottom of the table, which is sort of the bad stuff, linear classifier. So this is pairwise linear classifier, so that would be like the, not the one versus rest, but the one versus one classifier we talked about. That's getting like 7.6% error rate on this data set. Okay. Whereas if you train convolutional neural networks, and in fact here, this is an ensemble of 3 of them. We'll talk about all that stuff later in the course. You can get down to 0.09% error rate. And maybe even better, like I said, this is not a problem that really people care about that much, so I don't think a lot of people are trying to get, state-of-the-art performance in this, but it's as you can see, there's quite a range in the power of different methods. But the reason I'm bringing this up is that in this unit, we're going to be working on support vector machines, and although these are certainly not state-of-the-art by today's standards, they're pretty good. You can see this is 0.56, so way better than this linear classifier down here. So this is sort of a partial motivation to learn about these methods. And before neural networks got popular, these were at some point they were state-of-the-art. Maybe in the maybe in the 2000s, somewhere in there. This is what people were excited about. So that's sort of what we're going to be focusing on. But first, we'll talk a little bit about just these images themselves, how we handle the images in NumPy, and then we'll eventually get into more about the support vector machine. So just sort of starting with the images, like I discussed before, when we work with grayscale images, each pixel is going to be a value somewhere between 0 for black or 255 white, integer values. And we can essentially think of images as either matrices or as vectors. So if we want to view the image like this, these MNIST images would be 28 by 28 matrices of real numbers, where the real numbers, as they're stored, are integers. But when we take them into NumPy, we can convert them to floating point, and we can work with them there in floating point if we want. But it's a little bit easier to represent those images by flattening them. And that just means essentially extracting either rows or columns and stacking them front to back. So the way that NumPy does it, it depends on the language you're working with, whether it's done row-wise or column-wise. So NumPy is one of these languages, or Python is a language that does things by rows. So when it takes this image, it extracts one row, and then that puts that here, and then the next row puts it next to it, and so on. But if you work with MATLAB or some other languages, it's done in columns, something to be aware of when you're working across different languages. And also when you read papers and books about matrix algebra, you find that in papers and books, it also tends to be done by stacking columns. So if I write something in math format, I'm going to assume we're doing it column-wise, but we have to keep in mind that if we're using NumPy and Python, it's being done row-wise. Okay, so to be specific about the math, so let's say that I have this matrix with these elements in it, and if I vectorize that matrix, so this is what the vec command is doing, it's basically taking this first column, and that gives you the first 28 entries of this vector, then the next column it stacks below that, and so on, until the very last element here is this element there. Or if you start with this vector and you want to put it back into this matrix, here we're using this mat command to sort of go from the vector back into the matrix. And if you think about, well, what is NumPy doing then? Essentially, NumPy, you could say it's using the same commands, but it transposes that matrix before it puts it into the vector operation. And then maybe what you get out is a row also. So just a way of sort of describing what happens in NumPy using matrix algebra. Okay, so that's, and then there's actually a number of different commands that can go from the matrix to a vector in NumPy. Ravel, flatten, or if you reshape something, and this is basically saying reshape down to a 1D vector, and when you put a -1 into the reshape command, it basically says, you have enough information to figure it out. I don't need to tell you what that number is. And so in this case, like if NumPy knows the dimensions of a matrix and you want it to reshape it to a vector, it can figure out exactly how long that vector is, so that's why you don't have to tell it explicitly. But just the fact that there is one number here means it's going to be some 1D array instead of like a 2D array or 3D array. Okay, and then to go back, this is how you do it. You start with this vector, and now you reshape it into a 28 by 28 matrix to get this image that for us humans is a lot easier to understand. We can look at this and we can see a 7, but if you look at the rasterized image, we can't really make sense of it. Okay, so that's a bit about how we work with these images. And if we want to plot one of these images in Python, then we're again going to use the same matplotlib library, and imshow is the main command for plotting an image. And here we have just a little function that we wrote that takes in a vector and it reshapes it to 28 by 28. It plots it, and here we have to tell it like basically what colors do we want to assign to the different real numbers, and this is using the grayscale color map, which is what we want for this to get images that look like this. And then we're removing the ticks. If you didn't do that, you'd see like little ticks on the X and Y axes. So that's the little plotting command that we made here. And here's a little bit more about the data. When you download MNIST, the .data contains those images, and it's basically a big big matrix X, where every row in the matrix is a rasterized version of one of these. So the matrix would have 70,000 rows, right, and 384 columns, because there's 384 pixels in each image. And then the targets are going to be numbers from 0 through 9. And at some point in the code, it's important that these are represented as 8-bit integers, so that's why we're sort of forcing that in this line of code. And this is just going to extract some random digits. So I believe that a lot of the ways that MNIST is stored, it's actually ordered so that like all the first few rows are zeros and then come all the ones and so on. And if you don't shuffle those rows and you just train on the first part, you'll only learn how to deal with like zeros and ones and twos or so on, and then you try to test on the later rows, it's not going to work because it's never seen this. So it's important to shuffle, and that's what we're doing here. We're just basically drawing some random integers to do that shuffling. Okay. All right, any questions so far? Okay, so so the first thing we can do just is to see how well this works is we can try the best technique that we learned so far for classification with 10 different targets, and that would be multinomial logistic regression. So let's try that. And because this is kind of a big data set, it takes a bit of time to actually learn the weights and the biases. We're actually going to just focus on a smaller subset of 10,000 samples. We'll use 10,000 samples for training and then 10,000 for testing. And we have to do a little bit of pre-processing when we work with images usually. So what we're doing in this line is we're taking those, remember these are unsigned integers between 0 and 255. We're dividing by 255 to get an integer, a floating point between 0 and 1. Then multiplying by that by 2, so now it's between 0 and 2. And subtracting 1, so now it's between -1 and 1. So we basically have just normalized all the images so that the pixels live between -1 and 1. This is a very standard thing to do in image processing. It's a little different from the standardization that we've done so far, because in what we've done so far, every feature is standardized in a custom way, right? We learn the mean for that feature, we learn the standard deviation for that feature, and then we standardize. And that would be like doing every pixel differently. But if you shifted and scaled every pixel differently, what you would get would no longer look like an image. It would look pretty weird. And so that's not typically what's done when standardizing images. You tend to treat all the pixels the same. So basically, we're just doing a constant scale and shift of all pixels so that they eventually live in the range between -1 and 1. And you have to be a little careful when you do this. For example, if you do something like this, 2 times x divided by 255, this is actually going to fail. The reason why is because if x is an unsigned integer and you multiply it by another integer 2, you'll actually overflow, right? So it will basically the brightnesses will wrap around, you'll get garbage. And so it's important to do this floating point division first so that you get a floating point number, and then you can scale it by 2 after that. So yeah, so there's these little details that sometimes you learn the hard way if you don't do them right. Okay, so we got our training data, we normalized all our data, and we can run logistic regression. I don't remember what the default solver is, but we're going to use this one, LBFGS, which is supposedly a pretty fast solver. Using a pretty, I don't remember exactly why that regularization on the L2 was chosen, but when we do this, we get 90% accuracy, which is kind of maybe expected. If you remember, there's that table we saw earlier that was showing like 7.9% error rate. So this is 10% error rate. And it's a little bit worse because we didn't use the full data set. We didn't tweak all the parameters to try to, so it's sort of in the ballpark of what we would expect. But still, 90% is not really great. In fact, humans can do a lot better than 90% on this data set. And if you look at some of the mistakes it made, these are things that we as humans would probably not make mistakes here. So for example, this is a true digit 9 where it guessed a 1, true digit 4 where it guessed 8, 9 it guessed 3, and so on. So part of our motivation for doing all this is to try to understand a little bit about maybe what's going wrong with logistic regression, and then maybe propose something else that might work a little bit better, which will lead us down the path of the support vector machine. So that's our goal. So, all right, so let's just first review a little bit about multinomial logistic regression. It's not a bad time to review it. It's never a bad time to do some review, just to kind of understand a bit about how it works. And again, this is all stuff we learned in the last unit, but this is what we do. If we want to classify a test vector X, which would be a flattened MNIST image. So for each class hypothesis K, where now K goes from 1 through 10, we would design some parameters, Bk and Wk, and we know that when we design the kth parameters, we're trying to classify that image as either in class K or not in class K. That's the one versus rest idea. And so once we've trained those, the weight and the bias, and we plug in our test image X, we're going to compute a score Zk. And we're going to do this for each one of our classes. So we're going to do it for class 0, let's say digit 0, the class 1, which represents, let's say, digit 0, class 2, which represents digit 1, and so on. We're going to get a vector of scores. And now we're going to look through those scores and see which is the largest score of the 10 different scores. And if the third one is the largest score, we will say, okay, we believe it's class 3. And one of the ways to understand that logic is we have built a probabilistic model which says what is the probability that the class is K given this test feature vector. And then when we did MLR, we said, in particular, we're using the softmax as that probabilistic model. So that was this ratio of e to the power zk over this normalizing constant. And so if you do this and you just sort of look through all the classes to see which is the most probable, equivalently, you're looking through these softmax values to see which is the most probable. Well, they all have the same denominator, so what's really changing is this. And if you want to find what is the largest value of e to the power zk, you may as well just look at which is the largest of the zk's itself. Exponentiating it doesn't really change anything about which is the maximizer. So as we know, we can think about maximize the probability, or we could just think about maximizing the score. And either of them, they're both basically equivalent. So this is just sort of a recap of what we do in MLR. And if we want to draw this as a picture, it goes like this. So you take your, this would be your test image. You flatten it, you convert it to a 784 dimensional vector. You multiply it by a matrix W that contains all the learned weights. So for example, the first row in this matrix corresponds to the first class, digit 0. The second row corresponds to the second class, and so on. And then we have a vector of biases where we have 10 different biases. And basically you sum those two numbers together to get your scores. Vector scores, now we have 10 different scores. And if you want to know which class it is, you just look through that vector and you find the location of the maximum value. And that is your guess of the class. That's your K that you guess. So anyway, does this sort of make sense? Any questions on anything here? Yes.
So the data set you are using, you are assuming that, okay, the numbers are in the center and they are not rotating. So if that's not the case, would that put any effect on accuracy?
Sure, yeah, that's a good point. So this particular data set was very curated in that it was, when they collected the data, they made sure that all the numbers were in the center, that they were all the same size, that they were all rotated in the correct way. And so you could imagine making the problem more difficult by adding some, by breaking some of those invariances. You could change the size of the digits, you could shift them around, you could rotate them. And yes, all those things would make the problem more challenging for the machine learning model to handle, because it would have those extra degrees of freedom. And so you would tend to see the performance decrease. So that, yeah, that's true. But, you know, I guess every data set, like, there's some sort of balance between, you kind of want, when you create a data set, you want to remove, you don't want to, like, take out things that are important. Like, if it was very important for your approach to handle different sizes, then, you know, by making your data set all the same size, you would probably not be building a very robust approach. Or if it was important to handle rotations, then, you know, maybe you would want that in your data set. But if you can kind of justify that, no, we just want this, like, maybe easier problem, and we have other ways of adjusting the size of the digit. Maybe there's another algorithm that comes in and does that for you beforehand in, you know, when you're applying it, then maybe that's good enough. Okay. All right, so, okay, so if everyone's okay with this, let's try to think about what do we want these weights to look like. So let's take this case where the true digit is a 7. And so that would mean that the true k is down here. It would be like k equals 8, I guess, would be corresponding to digit 7. And so that would mean that if our system is working well, when we looked through this z vector and we came to this position k, that value is the largest, right? We want that value to be big, but all the other ones to be small. So what should this vector here of coefficients w look like, roughly speaking? If this vector x had a certain pattern of brightness values, what would you expect the corresponding 7th row of w to look like? If you want this one to be large and all the other ones to be small, just from an engineering perspective. Any guesses? Wouldn't you want to have a similar pattern manifest where you would, like if there was some bright spots, you know, large values in certain indices, wouldn't you want the same values here to be large? So that when you do this inner product, you get a large output. And then when you looked at a different row, it would have a different pattern of large values. And when you did that inner product, it would then be small. That would be ideal because then you would get a large score in the true k and small scores elsewhere, and that would be like a robust, you know, detector of that 7. Yeah.
I might have missed this, but is it just zeros for where it's black and ones for where it's white?
So more or less, I think it could be that if you look closely, there may be some gray values. I don't think it's all ones and zeros. There could be like at the edges some like something in between. Yeah. So but more or less, yeah, you could, and actually if you remember the way that we standardized it, it's a little bit different in that actually the black is now -1 and the white is 1. And then gray would be 0. But yeah, I mean, you have the right intuition. For the purpose of the discussion, we could imagine that yes, like black is 0 and white is 1. And so we're going to get some kind of pattern here. And now not every 7 is the same, right? So that's what makes it hard, is that there's going to be variability in the 7s, which means there's variability in those patterns, and thus we want to find a W, which is a good match for most 7s, but a bad match for all the 6s and all the 5s and so on. So that's sort of just intuition about what we want to happen with those weights.
So WT, that matrix is the coefficient matrix?
That's right, yeah, these are all the weights. So each one of the rows has the weights for every pixel. And if we're looking at, let's say, at the first row, that would be for class 1, k equals 1, or like digit value 0. So that's how this one versus rest, that's how we do one versus rest classification, is we make a bunch of different vectors, W, where the kth vector says whether it's in class K or not in class K. It's like a linear classifier for that binary problem. Okay.
And X is the test data.
Yeah, in this case, X is the test data, and then the Z would be like the test score, and we want to make a Z vector where the largest value is the one for the correct class. Yeah. Okay. So now that we understand that, we also said how it's kind of difficult for us as humans to look at this flattened vector and make sense of it. So similarly, it's going to be difficult for us to look at this flattened vector W to make sense of it. But if we have a way of just mapping this back to an image to make sense of it, we could do the same thing with these rows, right? We could just map them back to images, and we could look at them in the image domain. And when we do that, this is what we get. And there's actually two different experiments here. The first experiment is we used only 100 images for training. And in the second experiment, we used all 10,000 images for training. And now these are the learned WK rows, but repacked as or reshaped as an image so that we can interpret them well as humans. And when we do this with 100 training samples, we see the kind of patterns that we might expect, more or less. So let's say if we look at the row of the W matrix that corresponds to detecting whether it's a 0 or not a 0, you can see that it has, so remember, gray values, I believe gray would be kind of like 0 values. White here would mean like a positive value, and then black would be a negative value in the weight vector. So you can see that it's trying to emphasize, any pixels in X in this region is basically putting a large gain on them. And any pixels X in this region, it's giving a negative gain. It's like, I don't like that. I'm going to decrease my score for that. And then out here, it's basically neutral. It's applying 0 to those pixels and saying, I don't really care what's out there. Meanwhile, if we have a 1, it's really, strongly weighting those things, but then things just outside it, it's saying, I don't want to see that, and so on. And you can just visually see the images pop out when you look at the trained weight vectors, at least when you use 100 training samples. So is this making sense, what we're seeing? Okay, so the kind of interesting thing is when you look at 1,000 training samples, you see that those pictures got a lot weirder, right? It's very hard now to see like a 0 in here or a 1 or a 2. And essentially, why? What's happening here? Why did it learn these patterns, do you think? Well, okay, but like why did the pattern change to look like this?
Because a bunch of people draw them differently, so you just get a bunch of
Exactly, right. Because here there's like 100 zeros, they're all kind of similar. And then you're getting all these sort of weirdly shaped zeros that are, and also like this is trying to differentiate between zeros and all the rest. And so this is, dependent not only on the zeros for training, but all the other images. And you can see that it's basically, it is overfitting. It's doing something where it's like looking at very specific pixel values. It's like, oh, if this pixel is bright, then that's really important for detecting a 0, right? Or if this pixel is bright, that means it's probably not a 0. So it's kind of weird. It's done something that is a bit non-intuitive. And you could interpret it as some form of overfitting where it's really like, it's trying very hard to look for all these intricacies in the particular structure of the data. And perhaps, perhaps that's not what we want. Maybe this is a motivation for us to say, is it really important to look at all the data points, all your training points, or should we be looking at just a few important training points, learning from those and not getting distracted by a lot of other ones that maybe aren't as important to us? So that's sort of what we're trying to motivate here. Can we focus on only the few most important training samples? This is sort of just like a new design philosophy. And that design philosophy is kind of underpinning what the support vector machine is doing.
The second
No, that's a great question. It actually turns out that the second one does work better. So in that sense, it's, maybe it's not exactly clear why, why exactly. I mean, yeah, it saw a lot more data, it learned these more sophisticated patterns, and it does work better on the test samples. So in some sense, like, it looks like it's overfitting, but actually, maybe this one is, yeah. Anyway, it's hard to really read into the details too much, but it's just an interesting observation, and this is sort of giving us the idea of maybe that some of our training samples are more important than others in terms of learning classifiers. And that idea is sort of a powerful idea that does underpin a lot of strategies in machine learning. So that was the main message here. Any questions on this? Okay. Okay, so what we're going to do next is we're going to come back to our.
So is that of the images we're looking at, is that the graph version of the data set that we're done training the model?
These are the weights.
Weights.
Yeah. So we're plotting the rows of the learned weights once they were reshaped back into images for our human consumption. Yeah. Okay. All right. So okay. So that's sort of like giving us some inspiration to think maybe a little bit differently about how we design machine learning models, and now with that we're going to sort of change gears and come back to very simple kind of fundamental ideas about linear classifiers and just being able to visualize them and understand a little bit more about what's happening. And this sort of material here, we could have learned this back in the last unit. We didn't really need to get into the details, but we actually, I think in some of the homework problems for the homework that's due today, you were already sort of making pictures like this, right, where you were asked to plot a few points from your training data set and then to draw a classifier boundary and then to make some kind of inferences about what's happening, what can you learn about the coefficients that correspond to that boundary. And so now we're going to get a little bit deeper into those ideas and look a little bit more carefully at what's happening and to try to understand the geometry of these linear classifiers, and that's going to lead us to finally be able to formulate this new approach to classification called the support vector classifier. So let's just start at the beginning. And we have data here. This is in 2 dimensions. For us as humans, it's much easier to work in low dimensions like 2 or 3. 2 is the easiest. The ideas that we describe here, they will hold in higher dimensions, but it's enough to look at them in low dimensions like this, 2 dimensions. So we have, you can see 2 different features, x1 and x2. Binary classification, we have 2 classes, red and blue. And here we have our classification boundary. This particular set of data, the way that it's drawn here, you can see this is linearly separable in that this boundary has perfectly separated the data into red versus blue. But again, coming back to first principles, the important thing about the decision boundary is that it is the set of points. So it is the set of x values such that, that's what this dot means, such that B plus X transpose W, which if you remember, that is the score Z, such that the score Z takes on the value 0. So that's the thing to remember about the boundary, is for all the possible feature x1, x2 pairs on the boundary, this is the place where the score is 0, which is the place where the classifier is most unsure of what to do, right? It basically has no idea what to do for data that's right on the boundary. The farther the data point is away from the boundary, the more obvious it is what class it's in. The closer it is to the boundary, you could say that's the more difficult data to classify. Okay, but anyway, this is an important equation because this basically tells us how do we define the classifier. Or the classifier boundary. It's the set of x values that force the score to 0. Okay, and as we know, this is a hyperplane, meaning it's some generalization of a plane in an arbitrary number of finite dimensions. So in two-dimensional case, it's a line. In three-dimension, when we have 3 features, it would be a two-dimensional plane. If you had 4 features, it would be a three-dimensional plane. It's hard to visualize it then, but it's always what we call a hyperplane. Okay, so the first important thing to note is that this hyperplane is orthogonal to our weight vector W. So here I've plotted the hyperplane, and here I'm plotting W as a vector starting at the origin and ending there. And the important point is that those two things are at right angles, the boundary and W. And so can we prove this? I think we can. So the way we can prove it is if we take any 2 points on the boundary, call them x1 and x2, we know that by the definition of the boundary, those 2 points satisfy this equation, right? For x1 and x2, b plus xi transpose w is 0. So imagine now that I have 2 equations, b plus x1 w equals 0, b plus x2 w equals 0. I can subtract those equations from each other, right? I can get another equation. If I subtract them, we get x1 minus x2 transpose w equals 0. Right? That gives us this. And if you think about what that means, it means that the vector spanning the difference between x1 and x2, which is exactly this boundary vector, is transpose w is 0. That means it is orthogonal to w. So that's just a short proof of how we can make this claim. Take any 2 points from the boundary, define the vector between them, and then by this equation that they must satisfy individually, you subtract these two, you get that orthogonality condition. So that's how we got there. Okay, so that's another important thing. Let's look at the intercepts. This is another important thing. In fact, if in a homework problem or an exam problem, I gave you a picture like this, and I said, what coefficients B and W1, W2 describe that boundary? Here's an easy way to do it. You look at the intercepts of the boundary and the coordinate axes. And when you look at this x2 coordinate axis, you know that the intercept must be minus b over w2. When you look at the x1 coordinate axis, the intercept must be minus b over w1. Okay, so why is that? So again, starting with this equation here, let's expand that out. So we have b plus, and then now let's kind of look at what's happening in here. We're going to have x1 and x2 are the coefficients in x, and w1, w2 are the coefficients in w. So if we write that out, we have x1, w1 plus x2, w2 equals 0, right? So that is always the case. For any values of x1 and x2, they must satisfy this when the point is on the boundary. And so now let's also say, well, in addition to being on the boundary, I also know that I'm on this coordinate axis, which means x1 must be 0. So if I set x1 to 0, then I know the equation has to satisfy that. And now you can see I can just solve for x2. And I will find that x2 is this value. Is that clear? So that's how we got that. Now, meanwhile, if I'm along this coordinate axis, that means x2 is 0. And so I take this term out, and now I say, what must x1 be? Well, x1 must be minus b over w1. Okay, so that's how we got this. Okay, so that's another kind of important realization. Now, of course, if you have a boundary that is like parallel to one of these, you can kind of imagine that as like taking this and then gradually moving this further and further out. So that's sort of like as W1 gets smaller and smaller, this thing gets larger and larger, right? And in the limit, as W1 goes to infinity, this will eventually itself be infinity. Which, as W1 goes to 0, this becomes infinity, and that is where you're going to get this horizontal line. So that's the case where one of these values, W1 or W2, goes to 0. And I think you saw that. If in the homework, if you looked at the solutions which created one of these horizontal classifier boundaries, then that corresponded to W1 being 0. Yes?
So if W1 is really close to 0, could you just assume that the x1 vector just is not really important to look at because...
Yeah. So if W1 is exactly 0, then that means that you are basically throwing away the x1 feature, right? That's what we want to do when we do feature selection, is exactly that. Yeah, that's right. Okay, so all right, so that's a next kind of important thing from this diagram. And I think the last thing to look at is if we ask the question like, how far away is a point from the boundary? And that's important, as we said, because if a point is very far from the boundary, in some sense, that's an easy point to classify. Whereas if a point is close to the boundary, that's a point that is more difficult to classify because it's closer to the point where we just don't really know what's happening. And if a point is very close to the boundary, then you don't know whether maybe there's just like a little bit of noise pushed it on the wrong side of the boundary, and in fact, the training data has some noise in it, so points that are very close to the boundary are just fundamentally kind of untrustworthy. They're difficult. So that motivates us to understand, can we compute the distance from a point to the boundary? And we're going to compute what's called a signed distance. So usually distance is just a positive number, right? But we can actually think of distance as being positive or negative depending on which side of the boundary we're on. So if we're on one side of the boundary, we could say that the distance is positive, and to a point on the other side, we could define the distance as negative. So the way that we can do all this is, let's say that I have a point xi here, and I want to know what is the distance from the boundary, and let's say that distance I'm going to call gamma I. So one way to do this is we know that if I'm going to measure distance from a point to a line, I have to move in the direction that is orthogonal to that line, right? Like if I said the distance from the point to the line is this, you'd be like, no, that doesn't make sense. That's not the right distance from the point to the line. The distance from a point to the line is like the closest distance. And if you want to get the closest distance, you have to move exactly orthogonally towards that line. So that's what we're going to do. We're going to define a unit vector by taking w, which we know is orthogonal to the line, and dividing by the norm of w. And now we have a vector pointing in the direction of w with norm 1. And we're going to say, how much gain do I need to put on that norm 1 vector until I'm sitting exactly on this line? That is how we're going to define the signed distance. Like, I have this direction I'm moving in, normalized, norm 1. How much do I have to move until I'm sitting right on the boundary? That is the distance. That is gamma I. So we can do that pretty straightforwardly. So when I'm on the boundary, the score is 0. So to get there, I take b plus here's my original point xi. This is, after I move, I get gamma I divided by w over norm w times w. Okay, so this is like This is the new point on the boundary. And as we know, if it's on the boundary, it needs to satisfy this equation, right? So here, I'm satisfying that equation, and this is my original xi, and now I've moved it by this much, and I just need to figure out now, what is the gamma I that makes this true? That is the distance from xi to the boundary. Is that idea clear? Okay, so basically, the rest is just a little bit of algebra, really. So we have, this is going to be equal to b plus xi transpose w. And then the next part here, you can see that we're going to have a w transpose w, which we know is the Euclidean norm squared, divided by the Euclidean norm, so that will cancel the square. And what we get finally is just gamma I times the Euclidean norm. Is everybody okay with that? So all I did is simplify this down to this.
So you have your direction vector,
Yes,
right? Because you have x in the direction of w, right?
we're moving in the direction, yeah, we're moving in the w direction.
Right? And then the value for x at that point after you use the direction vector is just 1, right? But then when do we get to that shift, like that offset where it moves down the other line? Like, does that make sense? Okay, so just look at the w, right? The w vector.
Mm-hmm.
After we do the direction vector for w, then my interpretation is that we're now by that orthogonal point, right? Where those two lines meet, like right in the middle, like the intersection.
So this is like, let's say that this is, I'll draw it in green. So this would be like, for example, maybe this is the unit norm W.
Yeah.
So what I'm going to do is now I'm going to take that green vector and I'm going to translate it over here. I'm going to put the green vector here. So for example, this point here would be xi plus w, right? That's what this point is. But I want to go over here. So I have to put a negative gain on this. And that will actually move me. If the gain was -1, I might be here. And maybe I need to make it like -1.2, and then I'm finally right here. Yeah, so that's all we're doing here. And essentially, we're just trying to back solve for the gamma I that makes this true. And when we know that this equals 0, we just basically solve for gamma I, and we get this. So this is the sign distance from the point xi, any training point, to the boundary. And as you can see, this could be positive or negative depending on the sign of the numerator. So that's why it's a signed distance. Okay. All right. And then very quickly, one last concept is, notice that if I take a b and a w and I scale it by alpha, I'm not actually going to change the intercepts, right? Because the alpha is going to cancel here and here. And so if I scale b and w, I actually have exactly the same boundary. So this is what we say, when two classifiers are equivalent, that means they share the same boundary. But if I like have a negative alpha, what's going to happen is I'm going to change the sign of this, which means essentially I'm going to be sort of changing. If for example, maybe if I start out by saying these are positive scores, these are negative scores, and you flip the sign on B and W, you end up flipping what you mean by positive and negative scores. So we don't want to do that. We don't want to flip polarity. We just want to keep alpha positive. But basically, for any positive alpha, we're going to get a classifier that's essentially equivalent, has the same boundary. The only thing that's different about it is the value of z when it's non-zero will be either bigger or smaller. It will be like we'll have more or less confidence. And so those are basically the important things we can learn by just taking a close look at this geometry. And then next week, we'll kind of get into how we can use this to design a new style of classification. All right, sorry I went over a little bit. Have a great weekend. See you guys next week.